So now let's talk about simple steam power cycle. Means basically we are interested in Rankine cycle, but first of all I will define what is the meaning of simple steam power cycle on which the steam power plant will works. So now we are interested in simple steam power cycle. So I will show the block diagram, and with the help of this block diagram we can easily understand. So here I am having the boiler and I am supplying the heat, that is suppose Q1, and then the steam produced, it is going towards the turbine, that is high pressure steam, high pressure, high temperature, high temperature steam. It is going into the turbine. So the turbine will do some work, say that is W, and for steam power plant means we are using the high pressure and high temperature steam, and we are converting into the mechanical work, and this mechanical work is used to operate the generator. So basically these are connected with the generator. So this one is nothing but generator, and this one is nothing but turbine. So after expanding in turbine, the steam will go into the condenser. Now the steam will go into the condenser. Here, this one is the condenser. So condenser. So from condenser means, what is the use of condenser? Means we are converting. First, we will decrease the temperature of the steam, and we will convert the steam into the water. So it will reject the heat, that is Q2, and now this water will be pumped through this pump. This one is pump, and again this water is going into the boiler. So again this water will going into the boiler. So this one is a block diagram which is representing the simple steam power cycle. So again I will repeat it. The simple steam power cycle, the on boiler we are giving the heat, that is suppose Q1, and due to this heat the water will convert into high pressure high temperature steam. Then this high pressure high temperature steam will be enter into the turbine, and this turbine will do work, and this work will be useful in generating the electricity. That's why we are calling steam power plant, because steam is using for generating the power. Then after expanding or doing work in the turbine, the steam will go into the condenser. Here in condenser, the temperature of steam will decrease, and at the same time it will convert it into the water. So now this water will pumped through this pump into the boiler again. This one is the boiler. So this one is nothing but, this is we have to give work, that is WP, and this one is WT. So here if you see, I will write some of the things which is very useful. Heat supply. Heat supply, that is Q1. Heat rejected, that is Q2. Turbine work output, that is WT. Then pump work, this one is WP, that is pump work. So we can say that net work output equals to WT minus W. So I can write that is W. W equals to WT minus WP. So here the net work done is WT minus WP. But sometimes we neglect the pump work if it is very small in comparison to the turbine work. So by this way we can also write down the efficiency formula. So efficiency is nothing but in the W by Q1. So I can write WT minus WP divided by Q1. So this one is a very basic theory for simple steam power cycle. So now I will define the Rankine cycle. Rankine cycle. Rankine cycle is nothing but a thermodynamic cycle. A thermodynamics cycle for steam power plant. So again I will draw quickly the block diagram for the simple steam plant. Here we are having the boiler, and then here we are having turbine. We are having condenser, and then we are having pump, and again we will reach up to boiler. So suppose we are entering, this position is 1, slaying position is 2, this one is nothing but turbine. It is producing WT work. Here entering at 2, leaving at 3, rejecting heat Q2. Here 3, 4 at pump. For pump we require WP. Then this 4 and again it will come 1 here. Q1 is supplied to the boiler. So now I will plot all these curves on a TS diagram. So that is representation of ideal Rankine cycle on TS diagram. So now I am having TS diagram. And remember one thing, here the phase of the substance is changing. Sometimes it's water and sometimes it's steam. So now we have to deal with this term, which is for phase of the substance. Now if you take 1 to 2, 1 to 2 is what? That is work done in turbine. So turbine work done is isentropic expansion, where the entropy is constant. So I will take some isentropic, means the entropy will constant. Suppose I am here at point 1, and now isentropic expansion means I will go straight vertically because entropy will constant, and suppose this point is 2. So 1 to 2, this one is the isentropic expansion. And now if you see 2 to 3 process, so what is happening here means the steam is converted into the water. So if you see, this one is nothing but the saturated vapor, and this one is nothing but saturated water. So this mixture will condense into the condenser and it will convert it into water at point 3. So 3 we are having water. 3, and this water is pumped through this pump. So 3 to 4, that is isentropic compression, because the pressure we have to increase. So here we are going for pressure increasing, that is a small one, 3 to 4. And if you see 4 to 1, that is nothing but constant pressure heat addition. So now for constant pressure heat addition, we are having this constant pressure line. So this line will come here. So now this is a constant pressure heat addition. So now I am showing this one is the ideal process. So 1 to 2, it's nothing but isentropic expansion, isentropic expansion. 2 to 3, it's nothing but heat rejection, that is Q2. W3, it's isentropic compression or pump work. And for 4 to 1, there is a heat addition Q1. So this one is a representation of a ideal Rankine cycle. But in practically, the expansion will not be isentropic, fully isentropic expansion, and the pump work will not be isentropic. So there will be some losses, or it will be responsible for increasing the entropy of the system. So now we will represent the real Rankine cycle on the TS diagram. So before discussion of a real Rankine cycle on the TS diagram, I would like to calculate the net turbine work, pump work on the basis of enthalpy. So I am just applying the steady flow energy equation. So according to our diagram, the steady flow energy equation for boiler, if we apply, then we will get Q1 equals to H1 minus H4. Just to refer the previous TS diagram, so we will get Q1 equals to H1 minus H4. Similarly, turbine work, that is steady flow energy equation for turbine. If we do like that, then we will get Wt equals to H1 minus H2. So by this way, we can get the turbine work. Similarly, now we will apply steady flow energy equation for pump. So here we will get Wp equals to H4 minus H3. So in that process, we have to consider the enthalpy at each and every step. If you know the enthalpy at each and every step of the substance, then we can easily calculate Q1, Wt and Wp. So we can easily calculate the efficiency. Efficiency is nothing but W net by Q1. W net is nothing but Wt minus Wp by Q1. And if you put these values in terms of H1, H2, H3, H4, we will easily get the efficiency value. So now, sometimes what happen, especially for the work done, we can use the formula, that is VdP. So if you know, in case of reversible adiabatic compression for the flow process, so we can say that, like I am talking about pump work. So pump work may be calculated by using reversible steady state flow work. So in that case, we already know Wp is nothing but H4 minus H3. So it is equals to VdP, because we know del H equals to VdP. So because we are having this formula, TdS equals to del H minus VdP, and here in the process of that is a isentropic process for the pump work, so TdS will be 0, so we are getting del H equals to VdP. So del H is nothing but a difference of enthalpy, that is H4 minus H3. Here we are also in H4 minus H3, so it will be equals to VdP. So in that process, we can calculate this WP, that is H4 minus H3, by this thing V3 P1 minus P2. So now V3 means the specific volume at state 3, and P1 and P2, that is the pressure. So by this way we can easily get the value of pump work if enthalpy is not given. So in the other words, if enthalpy is given, then straightforward we can calculate WP. But if enthalpy is not given, so if we know the specific volume and pressure, we can get the work done. Now I will give the real Rankine cycle representation on TS diagram. So let's talk about representation of real Rankine cycle on TS diagram. So now I will draw the TS diagram, and in that diagram I will represent both the ideal as well as the real Rankine cycle on TS diagram. So this one is our dome. So first I will draw the real cycle. So the real cycle I will draw. This is 1. This is suppose 2s. This is here 4. Here it is 4s. And then it is again. This one is the real cycle, actual cycle. So I will write here, say ideal cycle. Sorry, it's ideal cycle. Ideal cycle representation will be 1, 2s, that is 3. Sorry, this one is 3. 1, 2s, 3, 4s, 1. But what is happening here? Here we are using piping connections for passing steam or water from one place to other place. So there will be a piping loss. And in isentropic expansion and isentropic compression process, there will be no entropy change. Means we are considering the reversible processes for ideal Rankine cycle, but in reality there will be a irreversibility due to the external or internal irreversibility. So the entropy will increase. So if we neglect the piping losses, then and if we are neglecting the piping losses and we are considering the losses in turbine and pump, then our representation will be different. So I will show how we can accommodate this kind of losses in our actual Rankine cycle. Now I will represent the actual expansion process and the actual pump work. So the actual expansion process with increase in entropy is shown by 1, 2. The process that is shown by dotted line, that is 1, 2, that is actual expansion process. Similarly, 3, 4, it will be the actual pump work, 3, 4. So if you see from 3 to 4 dash process, there is a no change in entropy, but from 3 to 4 entropy is increasing. Means entropy of the universe will always increase. It's a realistic case. So the for 3, 4 is a realistic case. Similarly, from 1 to 2s, there is no change in entropy, but from 1 to 2, the entropy is increasing. It means it's a more realistic case. So I am now writing the cycle, which is actual cycle. So actual cycle here is represented by 1, 2, 3, 4, 1, 2, 3, 4, 1. So this one is the actual cycle. And remember one thing, here we are considering losses in turbine and pump. We are not considering the piping losses. Now we will discuss about effect of mean temperature of heat addition on efficiency. So now we will discuss effect of mean temperature of heat addition on efficiency, means the Rankine cycle efficiency. So now I am drawing here one curve, and then we will understand the effect of mean temperature or on heat addition or on efficiency. So here it is again I am drawing the TS diagram. So we know our TS diagram for the ideal, sorry, 1, and then 2 as we are representing for ideal. Now we are having 3, we are having 4s, and now this one is our ideal cycle, 1, 2s, 3, 4s, and 1. So now here we know the Q1. Q1 is nothing but H1 minus H4s. It is just a difference of enthalpy for this process. This process is a heat addition process from here up to here. That is heat addition process from 4s to 1. So we have to take difference of the enthalpy, that is H1 minus H4s. So now in terms of mean temperature of heat addition, we are giving heat from 4s to 1 here. 4s to 1 we are giving the heat. So now I am taking a mean temperature and I am again calculating. Suppose the mean temperature I am showing, that is here, that is mean temperature. So this one is suppose mean temperature, and we are representing with 5, 6. So this one is our mean temperature, that is T mean 1. So if we take mean temperature, then we can also write in terms of entropy, that is Tm1, and entropy, that is S1, and here we are having S4s. So I can write S1 minus S4s. So now Tm1 is nothing but H1 minus H4s divided by S1 minus S4s. So similarly, we can also find out Q2, that is heat rejected. Q2 is nothing but, here we are rejecting heat, that is Q2. So Q2, again we have to take the enthalpy difference, that is H2s minus H3. So in terms of mean temperature, I can write T2, or directly I can write, because it's a constant line here and this temperature is suppose T2. So I can write T2 S1 minus S4s, because this 2s and here 1, 3 and 4s all are having same entropy. So now we are having Q1 and Q2 in terms of Tm1, T2 and S1 and S4s. Now find out Rankine efficiency. So Rankine efficiency is nothing but 1 minus Q2 by Q1, that is general formula. So again, efficiency of Rankine cycle, I can write 1 minus, in place of Q2 I can write T2, S1 minus S4s divided by Tm1, S1 minus S4s. So now Rankine cycle efficiency will be 1 minus T2 by Tm1. So T2, that is the temperature of heat rejection. So this temperature of heat rejection will be the lower temperature. So for given T2, that is lower temperature, efficiency of Rankine cycle increases when Tm1 increases. So in other words, we can say that the higher the mean temperature of heat addition, higher will be the cycle efficiency. So in other words, higher the mean temperature of heat addition, mean temperature of heat addition, higher will be the cycle efficiency. Higher will be the cycle efficiency. So remember this thing. This is very important. If the mean temperature of heat addition is increasing, then the Rankine efficiency will also increase. Now I will define the advantage of reheating of Rankine cycle. So I will show here what are the effects of reheating on the efficiency or work output of the Rankine cycle. So here we are talking about reheat cycle. So I will just show the reheat cycle on TS diagram. So by TS diagram itself, we can understand what is the meaning of reheating. Reheating, as the name implies, in reheating we have to heat the steam more than one time. That is reheating. So here, what we have to do, we have to use two turbines. Like in first turbine, we will expand steam from one enthalpy to another enthalpy. Then we again send this steam to the boiler, and again it will reheat. And after reheating, again we will get work output from the next turbine. So there will be uh, two kind of work will be there if we are using two turbines. So by this way we can use more than two turbine also. So that is the meaning of reheating cycle. And now I will represent the reheating cycle on TS diagram. So let's see, here we are having a steam at state 1 and it is expanding from 1 to 2s, and after that it is again reheating in the boiler, so the temperature is again increasing and it is going up to the point 3. So this one is reheating 2s to 3, that is reheating. And now after this reheating, again it will expand in the next turbine. So it is again expanding in the next turbine and we are reaching here, that is suppose 4s. I will again explain. Initially we are here at state 1 and we are expanding the steam from 1 to 2s in first turbine, and then we are reheating from 2s to 3 in boiler, and again from 3 to 4s we are again re-expanding in the second turbine. So now from 4s it will pass into the condenser, so it will leave at this point, suppose 5, and 5 to 6s it is nothing but our pump work, and again it will heated it in that process. So we are having these processes. So This one is the cycle for reheating. I will show where we're reheating, and I will show its expansion in first turbine, expansion in first turbine, and this one is expansion in second turbine, expansion in second turbine, and here on TS diagram I am representing the ideal cycle only for our understanding, and this one is nothing but reheating. Here this one is nothing but reheating. So this one is the process, or I think from this diagram it's clear, but if you want the block diagram, so I can also draw the block diagram. Suppose here it's a boiler water is entering at 6s state and it is leaving at 1 as per as our TS diagram, and from 1 to 2s it will expand in a first turbine, that is at 1 it will expand in the first turbine, that is our, we can say that high pressure turbine, because here if you see why I am calling high pressure, if you see the pressure line, one is this, second one will pass through this, and for the other turbine, that is 3 to 4s, pressure is low, that is the low pressure turbine. So that is the difference between high pressure and low. So the steam will leave at point 2s here in the diagram, 2s. So now the 2s will be again passing into the boiler and it will exit the boiler at 3 stages. So now this 2s will again go into the boiler and then it will leave at 3. So 3, this one steam will again enter into the low pressure turbine. So now this steam will enter into the low pressure turbine, and from this, that is the third stage, after expanding we are having 4s, and this 4s will passing through condenser. So now here we are having the condenser, here we are having the condenser will reject the Q2. So now it will leave at state 5, and 5 will be entered into the pump. You have to give WP work, you have to work on that, and 6 says that is the state which is entering into the boiler. So this one is a typical block diagram for reheat cycle. That is 1, 2s, 3, 4s, 5, 6s, 1. So now if you see this TS diagram here, so now let's talk about work done. So here work done will be H1 minus H4s, H3 minus H4s. That is the turbine work. So in that case, the net work done will be higher if we compare with the simple Rankine cycle. Why? Because we are getting two turbine work. The pump work will remain same, but we are getting two turbine work, that is from H1 to 2s, that is H1 minus H2s and H3 minus H4s. So now if I talk about turbine work, so I can write H1 minus H2s plus H3 minus H4s. And if we talk about pump work, then it will be H6s minus H5. So in that case, the net work output will increase. So we can say that due to the reheating, the net work output will increase. But what about efficiency? If you see this thing here and here, so Here again the heat addition is more, so the efficiency will depend on work as well as the heat addition. So the efficiency due to reheating will only increase when the mean temperature of heat addition will be more. So now we are having two conclusions. So I am writing conclusion here. First, due to reheating, due to reheating, net work output, net work output will increase, will increase, will increases. Second, due to reheating, due to reheating, efficiency, efficiency will increase only when, only when, only when mean temperature, mean temperature of heat addition, of heat addition will increase, will increase. Because in our previous discussion we have already discussed that efficiency will increase only when the mean temperature of heat addition will increase. So here remember these things, due to the reheating the net work output will always increase, but the efficiency will increase only when the mean temperature of heat addition will increase.